Okay, here's the next lesson in the mechanics. Components of a vector from page 164. Vectors I and j are units in the x and unit vectors in the x and y direction. So what that means is I is one unit that way and j is one unit that way. So along the x-axis here. Unit vectors, 1 and 1. So we need to draw a diagram to show a vector OP with unit vector with x, x component 3 and y component 2. Okay, so there. That's that vector there. Look. 1, 2, 3. There's I, there's J, and there's 2. And that's P, and that's O, and that's OP. Okay. Right. So the vector OP can be written in component form or as a column vector. So O to P, you can either say it's 3i plus 2j, or you can say it's 3t. Okay. Suppose the vector O to P has magnitude r, direction theta, and components x and y. Let's just do that with a straight line. P, O, magnitude r, so that means it's the length is r. Direction theta, that would be measured from the positive x-axis. So what we can say is the x-coordinate. The x-coordinate is r cos theta, and the y-coordinate is r sin theta. R cos theta there, r sin theta there. Okay, so O to P, you could say it's r cos theta in the top part of the vector, because that's horizontal on the vector. That's the horizontal. R sin theta, that's vertical. Okay, so Pythagoras gives us r is the square root of x squared plus y squared. That's the x-coordinate. That's the y-coordinate. Tan theta is y over x. Okay. Yeah. So it's a good idea to sketch a diagram and find in theta, because 3i minus 2j and minus 3 plus 2j would give the same value as tan theta. So what that means is, if you've got 3i minus 2j there, and minus 3i plus 2j, which is over there, okay, the reason being tan theta for the first one, 3i minus 2j, tan theta is minus 2j over 3, which is minus 2/3, and that's this one here. This one here is 3i minus 2j. This one here is minus 3i plus 2j. So the other one, minus 3i plus 2j. Tan theta for that one is 2 over minus 3, which is also minus 2/3. So your calculator is going to give both of these two vectors the same angle, which they haven't got at all. This one has got that angle there, and this one has got that one there, and they can be completely different values. Okay. Right, so this example says express these vectors in component form. So we've got 6 at 50 degrees. At 50 degrees is going to be a bit like that. So that's the origin. That's 6. That's 50 degrees. So this is 6 cos 50 degrees. 6 sine 50 degrees. So you can say R is 6 cos 50 degrees in the I direction plus 6 sine 50 degrees in the J direction. Or you can say it's the vector 6 cos 50 degrees, 6 sine 50 degrees. And then B, if I don't draw the diagram, I think you can understand what I'm going to say here. R is 15 cos 223 degrees in the I plus 15 sine 223 degrees in the J. Or you can say R is 15 cos 223, 15 sine 223 degrees. Okay. Example 2. Work out the magnitude and direction of these vectors. These are the ones where you need to draw the diagram first, when you've got to figure out what the magnitude and direction is. So the first one is 5 across and 2 up. So it's going to look something like this. That's only rough. So this is P, which is 5i plus 2j. So we've got 5 in that side, 2 there. The magnitude of P is the square root of 5 squared plus 2 squared, which is the root of 29. The direction of P, we measure from, when we do bearings, and this came from the last video, we measure clockwise from the north. For these types of vectors, we measure anti-clockwise from the positive x-axis. So we say this is tan inverse, theta there, tan inverse 2 over 5, shift inverse tan 2 over 5, 21.8 degrees. Okay, now B, that one's A, B minus I minus 2j. So it's minus I minus 2j, that one's down there. So that's minus 1. And that one there, that's minus 2. Okay, if you did tan inverse minus 2, the opposite, the j component of the I component, it would give you tan inverse of 2, which is shift tan inverse 2, 63 degrees, 63.4 degrees. That, when we've got to measure from there, is not 63.4 degrees. It's because it's 180 to start off with. So what's happened, I sort of referred to this a bit in the previous page, the two minuses have cancelled out. So it's given us an angle in this quadrant when we want it over here. In fact, whenever the j component is negative, as in this one here, it will always give you the wrong angle. Because over here, look, the j component was negative down there. And if you do it on your calculator, sorry, it's if the I component is negative. If the I component is negative, so it's if it, I'll start with that again. If the I component is negative, so it's in this quadrant or this quadrant, doing this tan inverse will give you the wrong angle. Because if it's over here, it's going to give you the angle down here. If it's over here, it will give you the angle in this quadrant. So basically, if the I component here is negative, you've got to add 180 on to the angle that it gives you on the calculator, because then it'll give you the right angle. Okay, so the modulus of, that's Q. The modulus of Q is the square root of 2 squared plus minus 1 squared, square root of 5. The direction of Q is 180 degrees plus tan inverse minus 2 over minus 1. So it's 180 degrees plus 63.4 degrees, which is 243.4 degrees. Okay, so when you do the tan inverse, it'll give you this angle, it'll give you this part here, 63.4. But you want this full bit, so you've got to add 180 to the 63.4. Okay, so next one. When vectors are expressed in component form, to add or subtract the vectors, you add or subtract the I components and then add or subtract the j components. To multiply a vector by a scalar, you multiply both components by that scalar. So it's a P is 12i plus 5j. And Q is 3i minus 4j. And it says work out P minus Q, 2P plus 3Q. A vector parallel to P with magnitude 39. And the unit vector Q hat. Okay, so A1, P minus Q is 12i plus 5j minus 3i minus 4j, which is 12i minus 3i is 9i, 5i minus 4j is 9j. Okay, and then number 2, 2p plus 3q, this is 2, 12i plus 5j plus 3, 3i minus 4j, so it's 24i plus 10j plus 9i minus 12j, so that's 33i minus 2j. For these ones, A, you could have also done it in the vectors form, the column vector form. P, 12, 5 minus 3 minus 4 is 9, 9. And then 2, 2p plus 3q. So it's 24, 10 plus 9 minus 12, 33 minus 2. So when you do this, it's 2 times the top, 2 times the bottom there, 3 times the top, 3 times the bottom there. Then you add the tops and add the bottoms, but without being a minus, it ends up taking it away. That's part A. B, a vector parallel to P with magnitude 39. So we do the magnitude of P first of all. The square root of 12 squared plus 5 squared. Square root 144 plus 25, 169, which is actually 13. Okay, so 39 divided by 13 is 3. So the magnitude of P is 13. You want something parallel to P. By parallel, it means that the i's and the j's have to be in the same proportion. And 39 is 3 times the magnitude of P. 3 times 13. So basically, the vector we want is 3 times this. So it's 36i plus 15j. Okay, and then C, the unit vector Q hat. So what we do there, we say the magnitude of Q is the square root of 3 squared plus minus 4 squared. Square root of 9 plus 16, which is 5. So when we want the Q hat, That means we need a unit vector. We've got to divide by 5 because Q has got a magnitude 5. We want it to have magnitude 1, so we've got to divide by 5. And so therefore, Q hat is 1/5 of 3I minus 4j, which you can say is 3/5 I minus 4/5 j. Okay, I need this box. Well, we've got ABC. Okay. We can separate a two-dimensional vector equation into two equations, one for the x's and one for the y's, or the i's and the j's. So two vectors are equal if and only if their I and j components are equal. So example 4, got P is xi plus yj, Q is 2y plus 5i, and 1 minus xj. Work out the values of x and y for which P equals Q. So if P equals Q, then xi plus yj equals 2y, oops, don't want to underline that bit, plus 5i plus 1 minus xj. So if we look at the i's, first of all, we've got x is 2y plus 5. That's come from the I there is the I there. We don't need to write I, it's just part of it. Okay, and then if we look at the y's, yj is 1 minus xj. So therefore, y is 1 minus x. So now we've got simultaneous equations. Call that equation 1, that equation 2. So substitute for x in equation 2. So what I'm going to do is, instead of having x there, I'm going to put brackets 2y plus 5 there, because x is equal to this. So if I substitute this for x in there, I'll have an equation all with y's, and then I'll be able to work out what the y is. So if y is 1 minus, so instead of x, I'm going to put brackets 2y plus 5. So y is 1 minus 2y minus 5. So therefore 3y, actually therefore is better than improved there, mathematical. 3y, I've added 2y to each side, and then simplify the rest. The right hand side is minus 4, so y is minus 4/3. And then substitute for y back in 1. X is 2y plus 5, so it's 2 times minus 4/3 plus 5. So it's minus 8/3 plus 15/3, so it's 7/3. X is 7/3. Okay. So it's algebra basically. So we can work out what x and y are. We can work out what P and Q are using those values of x and y. Right, key point here, I've got the answer on the other side. If A and B, I'll just do this bit of writing underneath the bit I've just written. To describe the position point of A relative to an origin O, we use the vector O to A. This is called the position vector of A. It's called A underlined or RA. Similarly, we've seen that already actually. Key point, if points A and B are position vectors underlined A, underlined B, and to get from A to B, you've got to do B minus A, and the distance from A to B is the distance from B minus A. I'll draw a diagram of that to show what's going on here. Right, let's got A there, B there, A, B. Okay, so to get from A to B, there's A, there's B. to get from A to B, we need to go along there. So to get from A to B, it's that way there, we have to do a minus A, because we've got to do a minus A and then add on a B. Okay, so A to B minus A plus B, which we can write as B minus A. So it's the second letter, take away the first letter. So using the magnitude, the length of A to B. So the length of A to B is therefore the length of the vector B minus A. Okay, so example 5, points A and B are position vectors. A is 2i plus j and B is 5i minus 6j. I'll draw a diagram, but hopefully after I've done this example, you'll see that you don't need to draw a diagram every time. So 2i plus j is there, and that's the first one. And the next one, that's 2, so 5i minus 6j. It's not going to scale. B's going to be there somewhere. B. So A is 2i plus j. B is 5i minus 6j. Got it in the right sort of Y. So that's 2, that's 1. Up there, that's 5. And that's going to be minus 6 there. Okay, the distance from A to B. So let's start the vector that takes us from A to B. Is to get from A to B, look, let's go back there, minus A, B. That's A and that's B. So to get from A to B, I'll just go over that again. Get from A to B, let's go minus A, back that way, and then forwards that way. Okay, so it's a minus A plus a B. Or we can say, right, that's B minus A. So it's 5i minus 6j. That's the B, minus the A, 2i plus j. So it's 3i for the i's, and minus 6 minus 1j minus 7j. So the magnitude of A to B, that's the distance from going from A to B here, is going to be the square root 3 squared plus minus 7 squared. So it's the square root of 58. Okay, next one. Example 6. A, B and C lie in a straight line with C between A and B. Filling a diagram coming on here. So that's A and that's B. C's in between the two. And A to C and C to B is 2 to 3. That way. That's 2, that's 3. Points A and B have position vectors 2i plus 3j for the A and B, 12i plus 5j for the B. Okay, find the position vector of C. Okay, so because C splits this line in the ratio 2 to 3, this, if we can work out A to B, which we can because it's B minus A, this is going to be 2/5 of the difference, and this is going to be 3/5 of the difference. So let's do A to B first of all, which is B minus A. So I'll do it this way because it's a bit quicker. Save space. 12, 5 minus 2, 3, which is 10, 2. We've got all those numbers right. 2, 3, 12, 5, 10, 2. Yep. Okay. So find the position vector of C. A to C is 2/5 of A to B. So it's 2/5 of 10, 2. So that's actually 4. You do 2/5 times 10. You can think of it as 0.4 times 10 to 0.8. Okay. So, let's rub that out because I'm in that room. So A to C. So when we want the position vector of C, that we have to go from O to C. Let's suppose the origin is there. We want O to C. We know what O to A is. And we know what O to C is now. Okay, so O to C is actually O to A plus A to C. So it's O to A plus A to C. If you look where one vector stops, the next one starts. So this is going to be 2, 3 plus 4, 0.8, which is 6, 3.8. And you can write that as 6i plus 3.8j. A bit squashed there, not in a lot of room, but anyway. Okay. One more exercise. There's an exercise, one more example. It says, show that the point A, 0, 2, B, 2, 5, and C, 6, 11 are collinear. So the way to do this, you say A to B is collinear, means on the same line. So that means that A to B, A to C, which is longer, A to C is a multiple of A to B. So we do A to B, which is going to be 2, 5 minus 0, 2, which is 2, 3. A to C is 6, 11 minus 0, 2, which is 6, 9. I sometimes do that as a fraction. It's definitely a vector. Okay, so can you see that A to C is 3 times A to B? Look, 3 times 2 is 6, 3 times 3 is 9. Okay, so that means if you start on the line, if you do A to B 3 times, it's not very drawn to scale this, you'll get to A to C. So they've got to be on the same line because they're just in the same going in the same direction because they're proportional to each other. So you can say hence A, B, and C are collinear. That concludes that one.